Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we're going to learn how we can run a simple linear regression model in R. Before we start writing our code in R, I'm going to give you an introduction about this data set. This data set is from the book Essentials of Business Analytics, Chapter 4. It's called Butler with Deliveries, which shows the time that is taken for a trip. And it seems like this dataset is related to the type of trips that includes delivery of items in multiple locations. So for each row of data, you see the assignment that has been given to a truck or a car, the distance that is traveled, the number of deliveries on the way, and the time that takes to finish that trip. So from the physics, we know the simple equation of distance, time, and speed. If you travel with a constant speed, then the time of the trip is going to be equal to distance divided by speed. But this is not going to hold for our case because you have deliveries on the way and you're not traveling with a constant speed in most of the practical cases. So we want to come up with a more accurate equation using which we can predict time based on miles traveled. So we are looking for an equation that gives us a better estimation of time based on distance traveled. So in the first step, we assume that we only have miles. So deliveries is not a variable that we are going to include in our first regression model because we're just going to go over the simple linear regression model. So we're going to predict time based on miles, and we're going to do this in R. So I'm going to switch to R to explain how we set up the code. But before I switch to R, I saved this file as a comma delimited file or a CSV file. So you can go to File, Save As, and if your file is not already in the CSV format, you see comma separated values. It's one of the options that you have here in PC or Mac. You can find that option. So you save your file as a CSV file. And I saved it under Chapter 4 where I have all my files for Chapter 4 saved. So after you do that, we can switch to R and read this file into our R platform and start writing our code to run a simple linear regression model. Okay, when you open your R, there are two ways that you can work with R. You can interactively work in the console, or you can actually save your code in a new document and have it somewhere later on so that you can reuse it. So for the most part, I have a habit of writing my code on a R file and save it because I always can reuse it. The first thing you need to do to start running the regression model is to bring that file into the R platform. How R reads those files is by pointing the working directory or your folder in R to the folder that contains your CSV file. So there is a code in R called getwd. That this getwd just gives you the work directory. Basically, WD stands for work directory. When I run the getwd, I can figure out what work directory or what folder my R is reading off of. To run this line of code, if you're using Mac, you can hit Command and Enter and see it runs in your console. Or if you're in PC, you can use Control R. If you hit Control and push R button, whatever you read here is going to be implemented in your console. But here, right now, I just use Command Enter. I'm going to rerun it again, Command Enter. And you see that it's been implemented. So this is the work directory that right now R is reading your file, but my file is not in this folder. It's another folder that I have to introduce to R. The first step is to go to the location that you have saved the file. Now I find Butler with Deliveries CSV file that I want to use. If you right click and use get info, it shows you where the file is saved. So I'm going to copy this directory using Command C and switch to R and paste it in my R document. Now we have to change some of the stuff in this, but this is how you can get the work directory where your file is saved. If you're using with PC, there is an address bar on the top wherever you have saved your file, so you can get direct address to the folder by copying the address bar, which is on the top of your window. Now, in Mac, you don't need to change anything in your address, but if you're using PC, all your slash are backwards, so they're all this way. What you need to do, you need to change them all to /, but for Mac, you don't need to do that. So what I'm going to do, I'm going to define this as my work directory with some quotation at the beginning, at the end, because this is a text or it's a string of characters. So you have to put quotation at the beginning, then end. So this is my work directory. I save it as a variable called WD. So I can write a comment on the top using hashtag that defining my work directory. But this is where my work directory is, but R yet doesn't know where it is. So if I run this in the console using command enter, now I defined the work directory, but the work directory is not set to be this yet, because if I run the getwd command again using command enter, I see that my work directory is still is the old one. It hasn't changed to the new one. The way that you can set the new work directory to be the path that R reads your file off of, you have to use setwd. So when you use setwd, then you have to define when you want to set the work directory or your folder. Then you define the variable wd that contains the path to your file to be the work directory of your R console. So using setwd, you can set up your new work directory. If I run this line of code using command enter in my console, now the new work directory should be this. How can I check if it actually worked? If you run getwd, you expect to see that the path is updated. So I'm going to run command enter, and when I run that, you see the getwd shows that this is the new path. Now I'm good to read the file, read the CSV file, because I'm pointing to the right folder. Alright, now that your work directory has set up, you can start reading your file. So the file that we have, it's a CSV file, and the code to read the CSV file is called read.csv. So in that parenthesis here, you have to put the name of the file exactly as it is, which if I go back to my Finder, what I can do, I can copy the name of this file exactly as it is. Okay, so read.csv, and this is the name of the CSV file that I have. And now if I read this file and don't save it in any variable, it's going to directly bring it to the console, but I want to save it in a variable so I can reuse it later on and call the data again. So I'm going to save this as Butler. Butler is equal to read.csv, and that's the file name. So if I run command enter, you see that it runs and I'm able to read the file. Now, one way that I can check whether I was able to bring the file correctly into the console is using the head function. Head function basically help you to see the first few lines of your data. So I saved this in a variable called Butler, and I get head of Butler shows me the first few lines of the data set. Using command enter, I'm going to run this, and you see that this is what has been brought to the platform. So you have assignment, miles, deliveries, time, and seems like there are a few columns that have been imported from Excel to R as NAs, because if you remember, there was nothing after this. But we shouldn't be worried about this part yet, because we can refer to time and miles. These are the two variables that we need, and seems like they have brought up to the platform correctly. Another way is to check for the dimension, because we knew that the dimension of our data is 300 rows, right? 300 row, and we had 4 columns. So I expect to see the dimension of 300 by 4. So in this case, because there are more variables that are that have came to the platform, maybe you expect to see 8 variables. So let's look at the dimension. And if I look at the dimension of Butler, you see that it's 300 by 8, and that's what we expected. So the dimension of file is what we expected, so it seems everything has been imported over to the R platform correctly. Now the next step is to basically look at some of the basics of regression. So the first thing I want to see, is there any correlation between time and miles? Because if there is no correlation, there is no need for the regression model. The function that can help you to do that is called correlation. So I type in Butler and run that in my platform. As you see, since we have those 4 extra columns, you're going to see some NAs. If you don't want to get those NAs, what you can do after Butler, you can remove those columns and say Butler is equal to Butler with all the rows, but only columns from 1 to 4. So the first element is for rows, the second one is for columns. If you leave it empty, it brings all the rows of the dataset Butler. But 1 to 4 is for the columns. What are the columns you want to see? It's only 1 to 4. So if I run this, command enter, then get the head of my Butler again, you see that those NAs are removed now. So you get rid of those NAs that way. And if I look at the dimension of Butler, you see that the dimension of the Butler is 300 by 4 now. So you don't see those extra NAs that has been imported. Now if I go to the correlation, run the correlation matrix, you don't see again those NAs that are extra. So if I look at the correlation matrix, I see there is a almost high correlation between miles and time. It's around 70%, which is a high correlation. The assignment is not a variable because it just seems like it's just an ID in our file. But if I look at the miles and deliveries, the correlation is not so high. But if I look at miles and time, it's around 70%. And this is a symmetric matrix. If you want to get a visual of the correlation to see the trend and how miles and times increasing or decreasing together, you can use a function called pairs. Pairs is for the purpose of giving you a visual understanding of correlations. So if I run this part, you get a graph that shows all the variables that you have. We don't really care about assignment. So regardless of assignment, what we care is miles, deliveries, and time, and if there is any correlation between them. And as I said earlier, forget about deliveries at the time being. I just want to look at the correlation of time and miles. The way that you can read this graph is for any x-axis, you have to see what's in the bottom, written in the bottom, and for any y-axis, what is written on the left-hand side. So for example, this chart shows deliveries versus time. This one shows miles versus time. This one shows miles versus deliveries. This one assignment versus deliveries, and so forth. But if I look at the time and miles graph, I see a kind of increasing trend. As time increases, seems like the distance also increases, or vice versa. So it seems reasonable to set up a regression model that predicts time based on the distance traveled or based on miles. Another preliminary information that you can get from your data set is using the function called summary. If you type in summary Butler and run that using the command enter, you get the summary of all the columns in your data set. So we had assignment, miles, deliveries, and time. We don't really care about assignment, but for each of these columns, you have a lot of information, such as what is the minimum, what is the first quartile, what is median, what is the mean, what is the third quartile, and what is the max. So using this information, basically you can set up the box plot for the variable. And you have that for deliveries and for time. So summary gives you a very general idea of the data. For example, in overall, I know that the miles traveled in average are 70 miles, and the maximum and min are given, like the range of the distance traveled is between 40 to 100 miles. Same thing for times. In average, it takes 7.28 hours, but the maximum hours is 12.3 and the minimum is 2.8. Just give you a general idea about the data set. Now let's move on to running the actual regression model. So LM stands for linear model, and you have to write the variable name exactly as you see them in the data frame. So if time is starting with a caps letter, you have to put it with a capital letter. So we're going to predict time based on miles. And after that, we have to put the data name. What is the data set name? Data is equal to Butler. That's the name of the data set. So if I run the regression model and do not save it in any variable, using command enter, this is all the information you get. Basically, you just get the coefficient. You don't see any of the ANOVA table and the t-test for the variables. However, if I save it in a variable, then I'm able to get more information from this variable. For example, if you type in summary lm out and run this, you get not only the coefficient but also the standard error, the t-value, and the p-value, whether they are significant or not. As you see, in this case, both intercept and miles are significant variable, and therefore your equation becomes 2.42 plus 0.06 multiplied by your miles, which is the variables that you have. So summary lm out helps you to get basically more information out of your regression model. Your final equation is going to be 2.42 plus 0.068 miles is going to be equal to the time of the trip. So basically you have time equal to this. So if next time somebody travels 100 miles, it means that it's going to take 2.42 plus 6.8. So is more than 9 hours is going to take to finish the trip. And how do we know if it's a good model or not? R-square, it's a measure that gives you some sort of idea about how accurate your model is. Right now, your R-square is around 48%, which shows a linear model, but is not as strong. Probably there are other variables that are more important in explaining the variation in the system. The p-value for the whole regression model is 2.2 multiplied by 10 to the power of negative 16, which is really small, and therefore the regression model exists. It means that you have a regression model. That's your ANOVA for the whole regression model. So you have a regression model. Each of the variables are significant, so you have that equation as a predictor. But how good of a model you have is only 48%, is not a very strong model yet. Perhaps there are other variables that are important that we are missing. For example, the number of deliveries could improve the accuracy of the model. Is one of the variables that we can include in the next step to see how it can increase the accuracy of model in terms of predicting the time. Now, what I can do is also I can look at the plot of time versus miles and look at the regression model. So the way that it works, you can type in plot time. You're trying to predict time based on miles. And your data is Butler. And the next one is that let's put a title for our graph as well. So your main, which is the title, is going to be time, let's say, versus miles. And if I run this using command, it seems like I have a typo here. Okay, if I run this using command enter, this is the graph that you see, which shows the relationship between time and miles. But if you want to also see the regression line over it, you have to type in AB line. And then you have to put the output of your regression. So the output of my regression, I saved it in a variable called lm out, so I copy that here, and I want to change the color to something that it's not black, so I changed the color to red so that it's kind of easily identifiable when I run the code. So if you run that using command enter, you see the line is going to be generated on your graph, so that this way you can see the regression line. So what are the errors that we have? The distances of all these points from this line is going to be the error that we have in the prediction. This object lm output also contains a lot of graphs that can help us to identify outliers. To be able to see these graphs, let's partition our window, the plot window, into 2 rows and 2 columns. The function for that is called par. It stands for partition, and then you put mf row equal to the number of rows and columns that you want to have. So I want to have 2 rows, 2 columns. Basically, it allows a window of 4 plots. So when you run it, you get an empty window. But in fact, this window right now is separated based on this information. It's a 2 by 2 chart. So when you type plot lm out, which lm out is the output of your regression. It has a few plots, and 4 of them, the first 4 is going to be generated in here. So when you run it using command enter, you see residuals versus fitted, normal QQ, scale location, residuals versus leverage. But this one is probably the most important one because it shows you if your data following a normal distribution basically or not. So the more straight this line, the better odds of having a normal distribution. The other graphs, the other two, scale and residual versus leverage, is kind of to identify the outliers in your data set and remove the outliers. And the first one shows you the value of residuals versus the fitted value. So for any fitted value that you have, it shows you the error. And you can kind of get a sense of how the distribution of residuals work. If your residual shows a sort of pattern, you have to be suspect that there is another variable hidden in the data that is now included in your residual. So your residual contain the impact and effect of another variable that needs to be included in your original model. So if I look at this graph here, I can identify there is a point, like for example from scale location, 0.4 seems to be an outlier. If I want to drop 0.4 from my regression model and run the regression model without 0.4, so let's say you say lm, this is the variable that you want to save the new regression model, lm without 4 is equal to linear model of time based on miles, and your data is Butler, and your subset is equal to time that is not equal to 6.5. This is how the code change. You say lm without 4, you want to drop 0.4 from your data set, and if I go to my Excel spreadsheet, the fourth point has the time of 6.5. So it means that I'm going to run the regression model without 0.4, so time based on miles in the dataset Butler, but subset for time that are not. So this exclamation mark equal sign, it means not equal in R. So you say for subset of the data that time is not equal to 6.5. You might have more 6.5 in your dataset and you end up dropping more than one 6.5 from your data, which is fine because if 6.5 it's an outlier, any other data point that has the same time value is going to be an outlier. So if I run this, it runs the regression model without any point that has a time of 6.5. If I get the summary, my result has probably changed slightly. Now you see that your R-square actually has increased by almost 1 unit. So it goes from 48% to 49% by dropping that outlier from your data. Also, your coefficient has slightly changed. It means that you were able to improve the accuracy of the model. Your whole model still is significant as well. So just to recap over this code, we start by defining the work directory and setting the work directory, reading the CSV file, dropping the NA columns from our data, getting head and dimension of data, making sure everything transferred over correctly. Look at the correlation and pairs and summary to get the initial sense of data and see if our assumption for prediction of time based on miles makes sense or not. Then we run a linear model function for predicting times based on miles over the data set of Butler, get the summary of the output, and it shows all the information we need to conclude our regression model and get a sense of how accurate it is. We can use plot to plot our linear line and show how it fits the points in the space. Using partition, we can see all the plot that is included in the output of regression and get a sense of outliers and whether our residuals follow a pattern or not, and whether our data follows a normal distribution or not. And this part shows how we can run the regression over subset of data by removing some outliers or some of the rows in our data. With that, our lesson is concluded. Please refer to your Blackboard for your assignments. Thank you.